Okay, so today we're going to talk about transformations. Now, just a heads up, I was planning something different for this week with our Zoom meeting on Wednesday, I guess that was the 13th. Hopefully we would have already started transformations. We would have talked about reflections, and we would have talked about translations as well. I was just trying to remember what the plan was for that. We're going to move on. Today we're going to talk about something a little bit more complex than that. That was just the basic stuff. Let's get started. So again, we're going to continue chapter 6 today. So this is the very beginning of it, of course, during the Zoom. We will have talked about some of the earlier concepts, of course, just some of the more basic ones. The main focus for today is on two more complicated types of transformations, which are rotations and dilations. Here we go. So just a quick recap on transformations. Transformations are basically just where you change a shape into a new shape. That's about it, right? So transformations, they can be all sorts. Translations are the simplest one. Translations is just where the shape is moved left, right, up, or down, right? So this one right here is a translation because they just moved the original object to a new location to form the image. The image is the end result. A reflection is also pretty straightforward. It's just a mirror image of the object drawn across some line. Basically, all you need to know about that is you have your mirror line or your reflection line. All of your vertices, so the points in your shape, are the same distance directly from that line. That's what's important about that. So in other words, the further away it was from that line, the further away the image's vertex is going to be away from that line as well. Now, there's two others that we need to talk about today. Rotations, which the name is also pretty self-explanatory. It's where you just take something and you rotate it around a certain point. Those are really quite complicated. There's going to be something I'm going to have you jot down in your notes somewhere because it'll be really, really useful to make your life a lot easier. And then we'll finish off with dilations today, which aren't nearly as tough as rotations. We're not going to spend nearly as much time on that. But a dilation is just basically where you make an object bigger or smaller. So in other words, you're just either enlarging it or you're shrinking it down. Now, as with all transformations, the vertices of the new transformed shape are denoted with like a little apostrophe symbol. None of these, oh wait, yes, I was gonna say none of these have it in the picture, but this one totally does. Notice how this had a vertex of A. Once they rotated it, now the vertex is down here and it has like A with an apostrophe on it. You can call it A apostrophe, but just standard practice in math is when you see that apostrophe on a letter, you call it a prime. So I'd call that A prime. Same with this is the original B, it's then rotated, this is B prime, right? This at least tells us where the original vertices are ending up in our new transformed function. So it is really useful to get into a habit of doing. They should have done it on the other ones here, like if we called this A, then this one would be A prime. And if this was B, this would be B prime, and so on, right? Be sure you get into that habit. It's really, really important. All right, so rotations, here we go. So in Math 30-3, rotations will be done clockwise about the origin. Clockwise is just the standard way of doing it. If you so happen to see a question saying counterclockwise, then you got to think about it a little bit more, but always come back to the idea of a clockwise rotation. What I mean by that is a 90-degree clockwise rotation, like there is in this picture right here. It's 90 degrees. If you saw it from the origin, like if you drew a line from your vertex to the origin and then from the origin to your new point, that would form a 90-degree angle. A 90-degree clockwise rotation is the same thing as a 270-degree counterclockwise rotation. I don't know if they'll throw any questions like that on you, but it's just a good thing to note right now. So again, generally, we're just going to do these 90-degree, 180-degree, and 270-degree clockwise rotations. Now, the key thing about when you perform rotations, more so than ever before, it's important that you move just one vertex at a time. Don't try to do the whole shape all at once. I know it might seem tempting to do that, especially with a whole full rotation, but it's way easier if you deal with this one vertex at a time. I'll have a chart that I'm going to share with you in a second here that actually details how exactly you can do that, depending on whether you're doing a 90-degree, 180-degree, or 270-degree rotation, and I will have you jot that in your notes. And there it is. This chart right here, I would really appreciate if you jotted it in your notes, and believe me, you are going to want to, because otherwise you'll have to come back to this video every time you want to know how to do this. This is going to be an awesome cheat sheet for you, so if you haven't already paused the video, please do. But again, just to explain this, suppose you have a vertex A on a shape and A has coordinates x, y. So we're just being very basic here. It could be any x, y as your coordinates on that vertex A. This following table shows how to find the transformed vertex A prime. So if you were going to do a 90-degree clockwise rotation, how you're going to do it is you're going to take your coordinates and you're going to take the x-coordinate sign, so you're going to take the x-coordinate and change the sign. So if it was a positive number, change it to a negative. If it was a negative number, change it to a positive. The other way you could say that is you could say multiply it by -1, because that'll do exactly that. If you multiply a number by -1, it'll turn it from a positive to a negative, or if it was already negative, it'll just change it to a positive. Okay, so you can think of it that way as well. Anyway, once you've changed your x coordinate sign, then swap your x and your y. So the resulting coordinate relative to the original xy, after you do a 90-degree rotation, the original value of y will be your new x value, and your original value of x, except times by -1, will be your new y value. Okay, we'll look at this in greater detail in just a second. I know it probably seems obscure, but believe me, you're going to really like this table. Next one, a 180-degree clockwise rotation. This is the easiest one of the bunch. All you have to do is just multiply both your x and y coordinate by -1. So in other words, if they're positive, make them negative. If they were negative, make them positive. If one was positive and one was negative, make the positive one negative and the negative one positive. Okay, you just switch it around. Now, 270-degree clockwise rotation, it's very much like the 90-degree one, except you're changing your y coordinate sign, so make it positive or negative depending on what you had in the first place, and then swap your x and your y again. So your resulting coordinate this time, your new x coordinate will be -y, and your new y coordinate will be positive x, or just the plain old x you started with. Let's see an example. It'll make it a lot easier. So again, I've just kept the table on here, and I've got an example in the corner right here. A is kind of a silly point because A's coordinates are 0, 0. And if you had 0, 0 as your x and your y, no matter what kind of change you do to it, it's still going to be 0, 0. Because notice if y was 0, it's 0 there now too, and -0 is still 0. So we're not going to worry about A, right? Let's worry instead about, let's say C, just because it's out here. No, you know what? I'm going to backpedal on that for a good reason, because C's coordinates are 4, 4, and that could get confusing. I'm going to choose D instead. Notice D's coordinates are 3, 1, right? X is 3, Y is 1. Now, if we're going to do each of these rotations, hopefully you can see that a 90-degree clockwise rotation is going to bring us down here. A 180-degree clockwise rotation will bring us over here. And a 270-degree clockwise rotation will bring us over there. Because again, we're going clockwise the same way a clock moves. 90-degree, 180-degree, 270-degree. Okay? Focus in on this point D, 3, 1. If we're going to do a 90-degree clockwise rotation, according to this, we need to change the x coordinate sign. So we need to change it to a -3, and then swap your x and your y. So in other words, our new coordinate, D prime, is going to equal, make the x negative, and then switch them. So it'll be 1, -3. Okay, let's see if that worked. 1, -3, that's this point right here. That absolutely is your D prime, 100%, right? We moved that 90 degrees. So this little formula right here worked like a charm. You just make your x negative, just switch its sign, and then swap your x and your y. That's pretty much all you got to do, right? Let's look at the next one. I'll use like 2 primes to illustrate a 180-degree one. So we'll call it D double prime, okay? By D double prime, it says just take your original xy and make the x negative and the y negative, right? Well, they're both positive in the first place, so we can just times them by -1 to make them negative. So that should make -3, -1. Well, let's see what that looks like. -3, -1. So x is -3, y is -1. That's this point right here. That totally seems reasonable. If you imagine taking this little like diamond shape right here and start rotating it around, it seems perfectly reasonable that it would end up over here. So yeah, that is D double prime. The other thing you could check here, just because it's kind of interesting, imagine if D prime was your original angle. Well, to get D prime, or sorry, D prime is your original vertex. Sorry, not angle. Let's say D prime is your original vertex, and you're going to move it to where D double prime is. Well, that's a 90-degree clockwise rotation. So by that rule, you have to make your x negative, so make it -1, and then swap your x and your y. So it would be -3, -1. It's the same thing. It's the exact same thing one way or another. See how it works? It works all around. Anyway, let's find D triple prime now. D triple prime would be for our 270-degree rotation. That one says take your original y coordinate sign and make it positive or negative, like make it the opposite of what it was, and then swap them. So in other words, we need to make this -1 and then swap it. So it should be -1, +3. Well, -1, +3 is this coordinate right here. And once again, that seems totally reasonable if you follow the whole thing through, okay? Bottom line is, if you follow these steps, you can quite easily complete all of these rotations. And again, they always work when you're doing a rotation around your origin, which is how we're going to be doing things, at least for now, okay? Anyway, moving on. All right, so here's another example. Rotate the given shape clockwise 3 times, 90 degrees, 180 degrees, and 270 degrees. Okay, you have to deal with this one coordinate at a time. We're going to start with 90 degrees. Remember my 90-degree rotations. You take your coordinate, you make the x negative, and then you swap the x and the y. Well, this first coordinate for A is 1, 1. Okay, maybe I'll write that in here, 1, 1. Make the x negative, so negative 1. Swap the x and the y. That'll make it A prime. So let's start with our 90-degree one. Let's just organize our work here. A prime is going to equal 1, negative 1. Okay, so 1, negative 1 brings us to here, which seems pretty reasonable, and I'll label that A prime. Now, B prime, on the other hand, since B was originally 5, 1, once again, we need to make our x negative and then switch our x and our y. So in other words, that'll be 1, negative 5. So 1, negative 5 moves us straight down here. That's where B prime is going to be. Last one here, C. Let's say it's C prime now. C's original coordinate are 3, 4. So 3, 4. Make your x negative, switch your x and your y. That's going to make it 4, negative 3. So 4, negative 3. That'll put it right there. There's C prime. Draw your shape now just by connecting the dots. If you have a ruler, I'd highly recommend it. I'm just doing this freehand right here. And there you go. There's your original graph done with a 90-degree rotation. Now I'm going to change color here because I want to do the other ones in different colors just so they really stick out. Now I'm going to do the 180-degree rotation. So the 180-degree rotation just said you basically take your original coordinate and make each part negative, or at least times them both by negative 1. So this one's a little easier to do. I'd say A double prime is going to equal 1, 1. Well, now it's going to be negative 1, negative 1, right? So negative 1 puts it right here. So there's going to be your A double prime. Now for B double prime, once again, just take each of these and make them negative. So negative 5, negative 1. Negative 5, negative 1 puts us over here. That would be B double prime. Now for C double prime, once again, make each of these negative. So negative 3, negative 4. Negative 3, negative 4 brings us right down here. So that is now C double prime. And again, connect them with your lines. There we go. And I'll do one more color change here. We'll do purple, we'll say. How about 270 degrees now? 270 degrees, again, was very much like 90 degrees, except instead of making your x negative and then swapping, you make your y negative and then swap. So we'll start with A. We'll call that one A triple prime. Make your y negative, so negative 1, and then swap them. So that's going to be negative 1, 1. Well, negative 1, 1 puts it right here. That would be your A triple prime. Let's do B triple prime now. B triple prime is going to be make your y negative, negative 1. Swap it with your x and your y, right? So it'll be negative 1, positive 5. Am I right? Yep, I'm right. Negative 1, positive 5. I just had to double check that there. There you go. That's B triple prime. Last one here, C triple prime. Again, make your y negative, so negative 4, and then swap them. So it'll be negative 4, 3. Negative 4, 3 puts us right here. There's C triple prime. Connect the dots. So I'll do these, and then I'll do this, and then I'll do this. That's about all there is to it. Now again, remembering all those rules, I genuinely just had to remember them there. Remembering all those rules that I had in that table is going to be crucial. You can use your table. Your table can help you out. You can be free to use it while you're doing your practice questions, or even when you do the chapter test eventually. Please use it. It's really, really useful. It's important to know. All right, we're going to wrap this up today with dilutions now. This is going to be a lot easier than rotations, believe me. A dilution is where you either enlarge or shrink a shape. So it can go one way or another. You don't have to just make it smaller, you can make it bigger as well. Now, dilutions are done by multiplying all the side lengths by something that we call a scale factor. So a scale factor is just a number that tells us what to multiply our original shape side lengths by to make a new one. So if the scale factor is greater than 1, you're going to have an enlargement. If the scale factor is between 1 and 0, or in other words, you can just think of it as less than 1, you're going to have a reduction, or in other words, it's going to shrink. Okay? So this picture, of course, I just found this online. This is a scale factor of 2. This is your original shape. You multiply all your side lengths by 2. 6 times 2 is 12. 6 times 8 is 16. 6, really? Let me start that over again. 6 times 2 is 12. 8 times 2 is 16. 10 times 2 is 20. Hopefully you know what I mean. Anyway, moving on. Dilute the rectangle by a scale factor of 2 and list the new side lengths. Don't get confused with this word dilute. Usually when I hear the word dilute, I think it means like, you know, make it smaller or like drown it out kind of thing. In math, it just means multiply by your scale factor. So your scale factor is 2. This is a 4 by 2 rectangle. So our new one is going to have a side length of 8 and a side length of 4. So 8 by 4, let me just find a place on my grid here where that'll fit. I think it'll fit up here. This will be 8. and then by 4, and finish all the sides. I'm not doing very good with staying on the line here, but I'm doing my best. And I'll even like kind of half shade it in. There you go. Awesome. Now list the new side lengths. Well, if you're multiplying old side lengths by 2, your new side lengths are 8 by 4. That's all you got to do on this one. Next one, dilute the rectangle by a scale factor of 0.5. 0.5 is just what you're multiplying your side lengths by. 4 times 0.5 is 2. There you go. 2 times 0.5 is 1. There it is. And then I'll just shade it in as well. Your new side lengths, 2 by 1. Okay, you're just multiplying your side lengths. That's it. Now, if a new rectangle was drawn with the dimensions 14 by 7, what scale factor was used? Well, let's think about it this way. 14, of course, is the longer side. It's twice as long as 7. So 14 is going to correspond with this 4, right? So we can think of it as 4 times something is going to equal 14. Well, how can we find that something, that scale factor? Well, we just have to divide by 4. So in other words, this something, scale factor, is going to equal 14 divided by 4. Let's just plug that into a calculator. I'm pretty sure I know what that is, but yeah, it's 3.5. So our scale factor here, 3.5, I'll call it, is equal to SF for scale factor. 3.5 is your scale factor. That's what you would have multiplied all your side lengths by. And if you're not sure, if you really want to check, remember the original one had a height of 2. You can go 2 times 3.5. 2 times 3.5 is 7. And what do you know? That was the other side length. Nothing wrong with there. Last thing I want to mention on this before we call this video a day is when you use dilution, when you perform a scale factor on here, the shapes are actually like proportionate to each other, right? So all the side lengths are the same, they're relative to each other, they're proportional, but all the angles are going to stay the same when you do this. So don't go thinking that you're making some totally brand new shape. You're just changing the size of it, right? All the dimensions and stuff in terms of angles remain the same. All right, so for practice, this is an overlap of the questions I would have told you to do by the end of the Zoom. I want you to practice by doing page 221 to 239. I think I asked 221 to 229 for the last class. I can't exactly remember, but yeah, anyway, that's what I want you to do, page 221 to 239. Give that a shot, and again, if you have any questions from it, please let me know, and that's it. Anyway, best of luck.